Hey guys, let's go ahead and continue our discussion with the formal definition of a limit. So let's see a graphical interpretation of what the definition really means. So let's say we got our function f of x here. Here's y equals f of x. Here's the point c comma l. So that means x equals c is over here, and y equals l is over here. All right. So let's say that you come up to me and you give me an epsilon, and you say, all right, I want you to make the distance between f of x and L less than epsilon. So this is what you want. Okay, you want to have this. You want the distance between the y value and L to be less than epsilon. Alright, so what we're going to do is go over to our graph here and draw what this really is. So y equals f of x, whatever y is, it could be larger than L or it could be smaller than L, but we just want it to be less than epsilon units away. So it could be bigger than L, but it still has to be less than epsilon units away. Or it could be smaller than L, but still less than epsilon units away. Alright, so this interval here represents that. How do we know how big to make it? Well, we can just make it as big as we want. But remember, the idea is that epsilon represents really teeny tiny positive numbers. So technically speaking, the interval will probably just be really teeny tiny, smaller than this. But there's no scale on here, and also let's just blow it up a little bit so that we can clearly see what's happening. Okay, but the distance from the middle, okay, the middle is y equals L. The middle of this interval is y equals L, and the distance from that middle to either end is going to be epsilon. So we want y values inside of this interval, right? So that this will be true here. So basically, you come up to me and you say, okay, here's an epsilon. I want you to guarantee that the distance from f of x to L is less than epsilon. In other words, you want me to guarantee to you that the y value is somewhere in this interval. All right. So how do we guarantee that? Well, let's take this and move it over to the graph. So we're going to take this, draw horizontal dotted line, and now we're over here. Okay. So now we move this over to the graph. This point here. So the next step, now that we have that, is to take these and move them down to the x-axis. So we're going to take this, move it down to the x-axis. Alright, so now we're here. And then we're going to take this one and also move it down to the x-axis. So now we're here. Alright. So notice the distance from C to this end and the distance from C to this end are about the same. They won't always be the same if you're doing this kind of graphical example. But what we want to do now, we're looking here and we're looking here. So we're going to take, now we're going to pick a delta. Okay, so you've given me an epsilon, so now I'm going to give you back a delta. Because the idea is for any epsilon greater than 0, we can find a delta greater than 0, such that if x minus c, if the distance from x to c is less than delta, then the distance between f of x and L is less than epsilon. So basically, you've given me an epsilon, now I'm going to give you back a delta. So we've come this far. How do we pick a delta? Well, we're going to let delta be the distance from C to the closer endpoint. Okay, so here's one endpoint, here's another endpoint. We're going to let delta be the distance from C to the closer one. So they're about the same distance. Maybe the left one is a tiny bit closer. It kind of looks like that anyway. But let's just take that to be delta. So this will be delta. Alright. So the left one is a tiny bit closer than the right one, so this will be delta over here. Also a distance of delta. Alright, so basically, if we come back up here, now we picked our delta, and as long as x is in this interval here, then that guarantees that we're going to be on this piece of the function here, alright? And that's good because we want to be on this piece of the function. Because if we're on this piece of the function, then we know our y-coordinate is less than epsilon units away from L. Alright, so what happened here? Just to recap real quick. We had our function y equals f of x. You came up to me and you said, okay, here's an epsilon. Now I want you to make the distance between f of x and L less than epsilon. So what we do is go to our graph, we make a little epsilon interval here, so the distance from the middle to the top end is epsilon, and the distance from the middle to the bottom end is epsilon. Alright, so we know our y-coordinate can be anywhere in here. So how do we guarantee that that will happen? Well, we take our interval, draw horizontal dotted lines over to our function, okay, and now we take these points here and make horizontal dotted lines down to the x-axis. Alright, now we're surrounding the point C. So now we see, okay, we see which endpoint is closer to C. And whichever endpoint is closer, we want to let delta be the distance from that endpoint to C. Because we want to guarantee that the distance from f of x to L is less than epsilon, and we can guarantee that as long as the distance between x and C is less than delta. Alright, so we pick delta to be the distance from C to the closer one. The left endpoint was a tiny bit closer, so we say delta is this distance. So if we bring that over to the right, that's going to be this distance here, a little bit less than the distance from C to the right endpoint, right? So now we know, okay, we know that as long as this is true, as long as x is somewhere in this interval here, then we know that this is true, right? And if we look at our function here, bring it back up, then that means that we're going to be somewhere on this piece of the function, which is what we want, okay? So what we have is if, or this is what we've shown. We've shown that if f of x minus c is less than delta, then f of x minus L, absolute values, is less than epsilon. All right. So this works for any epsilon, all right? Because what you did is you came up to me and you said, here's an epsilon, just any old epsilon. All right. So whichever epsilon you picked, I gave you a delta back for it. So then we know that the limit as x approaches c of f of x equals L. All right. So that's kind of how the epsilon delta stuff works. It's pretty weird, kind of confusing at first, but the more you practice it, the more sense it'll make. So let's point out real quick, remember this is our point C comma L here, right? What happens if instead of being a solid point here, what if we erase that and make it a hollow point? So now the function f of x is not actually defined here, right? What changes? Absolutely nothing changes, right? We never used the fact that the function was defined here, and we have seen several examples over the past few videos where the function is not defined at the point, but the limit still exists, right? So this is sort of why that's allowed to happen, because the idea is that f of x can get as close to the value as we want, as long as x is close enough to some specified value c. So that's kind of the idea behind epsilon delta definition of a limit.